Welcome to the Space Telescope Public Lecture Series. Our topic tonight, how to hunt for distant worlds, with Emily Rickman of the European Space Agency and the Space Telescope Science Institute. I'm your host, Dr. Frank Summers of the Office of Public Outreach, and I always make sure to thank our amazing tech team, Thomas Marufu and Grant Justice, who take this recording and get it out to you. I will also note, as I do it every month for the last, I guess, about a year now, that the Space Telescope Public Lecture Series will be online only until further notice. Our upcoming talks include in July, Gwen Hart. If you were here last August, she gave the first volume of her Armchair Astrophysics. And this July, she will be coming back to give you a second helping of Armchair Astrophysics, the way to explore the universe, basically from the comfort of that Barca lounger. In August, we have our infamous TBA, which means that I have not succeeded in finding somebody to commit to August, but don't worry, I always do, and we will have a wonderful speaker in August. In September, we will have recipes for planet formation. Nicole Arulanatham, God, I got to practice that name, will be our speaker on September 7th. If you want details of these and other talks upcoming, you can go to our website for the public lecture series, www.stSci.edu/public-lectures. And on that page, you can see on the left that you can get the webcasts, both the YouTube playlist, as well as the webcast archive at the Space Telescope Science Institute. And you can also on the right see that you can subscribe to our email list. Also on our website are the list of the upcoming lectures. And if you click on those lectures, you will get the full details, including the full description. Also, after it has been recorded, we have the links to the STSCI webcast, as well as the YouTube version of the webcast. As I said, for the email, it's easiest just to sign up at the website, but I would also suggest that you want to subscribe to our YouTube channel, youtube.com/Hubble Space Telescope, all one word. You will get not only, you will get the new video notices of our new videos, as well as reminders of these live events. And if you have comments or questions that you want to ask, you can send them to the email publiclecture@stsci.edu. For those of you who want to follow us on social media, we have social media for the Hubble Space Telescope, for the James Webb Space Telescope that will be launching this fall, and just for the Space Telescope Science Institute in general. You can find us on Facebook, Twitter, YouTube, and Instagram at the handles listed there. I myself do a tiny little bit of social media, and if you want to hear what I have to say, you can find me on Facebook or Twitter as Dr. Frank Summers. And now our news from the universe for June 2021. Our first story, droning on about Mars. Actually, this is much more exciting than it sounds. So it was 1965, 56 years ago, when we got our first image from Mars. On the right, you can see the image that is, they put a television camera on Mariner 4, and this was the first image that came back. Now, that image on the left is actually a hand drawing of this image. What happened was the engineers and scientists were so excited about the first image ever from Mars that they took a computer printout of the values of the image and then went down to the art store and hand colored them in order to get the detail of what they were seeing on Mars. And they actually did a pretty good job. So we have been going back to Mars over and over in the years. And in the years since 1960, there have been 48 missions to Mars from the USSR, from the US, Russia, Japan, ESA, China, India, and even the UAE, United Arab Emirates. So there have been so many missions to Mars. And one of the reasons is that some of them have not really gone as expected. Mars is been an unlucky place to send spacecraft. There have been 24 successful missions of these 48 that I got on this list, but 20 of them were complete failures, and 4 of them were part successes and part failures. So we've been going back to Mars for, almost 60 years. And we're still going because there's still a ton of cool stuff to learn about Mars. The latest mission to Mars was Mars Perseverance that arrived at Mars on February 18th, 2021. And if you're a regular viewer of the series, I showed you this montage of 6 images back in March to say, hey, we're successfully landed on Mars. And also to do my normal little joke of, hey, it still contains rocks. Yeah. Well, Mars does still contain rocks. And here is a selfie of the Perseverance rover out there showing you some of the interesting rocks where it landed. It also shows you something new, something that has never been done before in all of the previous missions to Mars. That object in the background isn't a tripod for its selfie. That is the Ingenuity helicopter. And so as a special test case to see if we could fly on another planet, the Ingenuity helicopter went along on the Perseverance mission. And this is the video of that first flight of the Ingenuity helicopter, April 19th, 2021. And I've edited it to sort of zoom in, and now you can see the rotors starting up and getting up to speed, and it takes off. Now, this is the first flight, right? So they're not trying to do too much with it, okay? They're basically going up and then they're spinning at 90 degrees and hovering in the air, showing that in this very, the atmosphere of Mars is 1/100th the density of Earth's atmosphere. So, they really weren't able to really test this properly, in the atmosphere and in the gravity. And then it just goes back down, right? Now, that's not a terribly crazy flight, but you got to think about this. This is the Wright brothers moment for flying on another planet. This is really cool. The Ingenuity helicopter just rose up and came down. Now it's done several more flights after that, but this is the significant one. And I guess they call it a helicopter, but when you look at it, it really looks like it's just a drone, right? So hey kids, if you want to get your parents to pay for that really expensive drone you want, just tell them you're in training for NASA, that you want to fly drones on other planets. Maybe that'll work. Our second story today is a luminous blue anniversary. And this happens every year when we talk about the anniversary of the launch of the Hubble Space Telescope. That happened, the launch was in April 24th, 1990. And then the next day, Hubble was put into orbit by the Space Shuttle Discovery. This moment, by the way, has recently been commemorated with a Master Builder Lego set. This Lego set is 2,354 pieces, and it shows the Space Shuttle Discovery during STS-31, which was the launch of the Hubble Space Telescope, plus it has the Hubble Space Telescope as well. I know it has 2,354 pieces because my wife and kids and I put one together, and it's now sitting up on my dining room table. It's an expensive set, quite a long build, but well, for those of us who are science geeks, it's definitely worth it. But what the story is really about is about all the amazing Hubble images that Hubble has released over the years. And for the Hubble anniversary, they always ask us, well, give us something special. And we always go, oh my God, what are we going to do? What are we going to do? Well, each year somehow our image processors and our image selection team manages to come up with something really cool. And this year, for Hubble's 31st anniversary, the image is AG-CAR, a luminous blue variable star. Now, this is one of the most massive stars in our entire Milky Way galaxy. It's one of the 50 to 100 the brightest and most massive stars that we know about in our galaxy. And these stars are so so massive, and they're sort of at the end of their life, and they're in this variable phase where they actually blow off material. Okay, they get bigger and smaller, and then they actually blow off material, and it changes their brightness. And what you see in this nebula around it is the material that came mostly from an eruption about 10,000 years ago. So this luminous blue variable star is how we're celebrating Hubble's anniversary. The next thing they always do is say, well, can you put this into 3D for us? And my team and I, we work together, we go hem and we haw, and we research and find, and eventually we do it, okay? And so this video is a composite of a lot of work to take this beautiful image and turn it into a 3D visualization. So that's our visualization, A Flight to A.G. Carinae. We also produced two blog posts that explain how the image was produced, as well as a lot of the details, a lot of the much more detail than we've ever done before of the details how we turn that image into the 3D visualization. And you can find those at our blog, Illuminated Universe, at illuminateduniverse.org. And now our featured speaker. Emily Rickman is an astronomer at the Space Telescope Science Institute. She comes to us from the European Space Agency. She is an ESA Research Fellow, having previously been at Sheffield University, the Australian National University in Canberra, and at the University of Geneva. So she's a well-traveled astronomer, as we often get at the Space Telescope Science Institute. She tells me that she is an avid hiker and has enjoyed hiking here in the US, but that one of the highlights that she has had is that she skydived over the north face of the Eiger in the Swiss Alps. So not just an astronomer, but also a daredevil. Ladies and gentlemen, Emily Rickman.
Thank you so much. Let me just share my screen. Am I on the right screen?
Yes.
You're good, Emily.
Okay, great. Thank you. Thank you so much for the wonderful introduction and for having me here today. I'm really, really excited to be talking to you all about how to hunt for distant worlds. As Frank said, my name is Emily Rickman. I'm an ESA Research Fellow based here in Baltimore at the Space Telescope Science Institute. So really, to understand the context for hunting for so-called exoplanets or planets around other stars, we really have to understand the kind of history and everything leading up to this. But this definitely isn't a new concept. So, excuse me, there we go. So back in 300 or 400 BC, Aristotle once said there cannot be more worlds than one. And so this was already a thought that was going on way back in the Greek philosophers' time. But no one had really thought about this too hard or for too long in a very, very long period of time until we get towards the 1500s or so, where we start to think about like what planets could be like, or what other planets, other systems could be like. So up to this point, there was a very geocentric view of the universe. And many people believed that everything orbited around the Earth and that the Earth was the center of the universe, and didn't really have any other reason to believe otherwise. And it was Copernicus that came up with the theory that actually we orbit around the sun, which we now know to be true. But this was a revolutionary theory at the time, and this was in the 1500s, and it actually caused a lot of controversy in the world. But the whole thing was that we were starting to have this view of the universe that potentially that we're not at the center, and that maybe we orbit around other things. And if we orbit around our star, our sun, then maybe other planets orbit around other stars in the universe. This became even more exciting with the invention of the telescope. And I put this in quotes here because really it was the retooling of a Dutch invented spyglass in the 1600s in 1609 by Galileo, who was a very renowned figure in astronomy. I'm sure many of you have heard of before. But it was the invention of the telescope and turning the telescope to the skies that enabled us to actually figure out what we were looking at and whether this Copernicus theory is true. And so Galileo was responsible for the invention or the retooling of the use of a telescope. And this enabled him to discover the phases of Venus, which is in line with the Copernicus heliocentric theory of planets. But this also could be described by the geocentric theory from the years prior to that. So this wasn't really proof that we are actually in a heliocentric system. But when Galileo discovered that there were moons orbiting around Jupiter, the so-called Galilean moons, this was confirmation that not everything orbits around the Earth as once was thought. And so this was really the beginning of a revolution of understanding that there may just be planets in other systems. So then we fast forward a little bit to later into the 1600s in 1698. And this is the first documented piece of a scientist saying that there may be other planets, of actually considering what those planets might be like and what they may look like and whether they will have life on them. And so Huygens published in 1698 his Cosmophiros, of the speculations of the construction of the universe and the potential habitability of other planets. And so when we talk about exoplanets, it's a very new and exciting field, but actually this goes way, way, way back to these times where we can really start to think about how these things came about. Okay, so then we fast forward a lot to 1992. And this is when the first exoplanet was actually discovered. So this exoplanet is very interesting because it orbits around what we call a pulsar. And a pulsar is a remnant neutron star that's left over after a supernova. So after a star depletes all of its energy, all of its fuel, it explodes in what's called a supernova. And after this, you're left, for some situations, you're left with what's called a neutron star. And they emit these pulsars at very regular, periodic and timing that can be measured so accurate, in fact, more accurately than an atomic clock. And so if there are any perturbations to this measuring of the pulses that we receive from pulsars, then this could be due to a companion, so i.e. a planet or something orbiting around it, so that as they orbit around their center of mass. And this would cause the pulsar, the neutron star, to move towards and away from us. And then that would cause perturbations in the pulses that we're observing. And so that's exactly what happened in 1992, that the first exoplanet was discovered around a pulsar. And so then it was only a few years later, in 1995, which is kind of the sort of famous one that many people probably know about, was the first exoplanet that was discovered around a solar type star. And so this was discovered by Michel Meyer and Didier Queloz, who were at the University of Geneva at the time. And this was extremely exciting. So, I mean, the discovery in 92 was, of course, very exciting, but you would never expect to find life around such an object. I mean, pulsars emit such high radiation that life just would not be able to form around such a host. Whereas in this case, they were targeting stars that are very much like our sun, so similar in size, similar in temperature, and very much as we expect our own sun. But this was still this very interesting, very obscure discovery, which I'm going to talk a little bit later on, because what they discovered was something that wasn't really in line at the time with how we expected other stellar systems to look like, and did not look like our own solar system. But this is extremely exciting, and it was just in 2019 that Michel and Didier were awarded the physics Nobel Prize. And as a University of Geneva alum, I was very happy and very excited to have been there when this was awarded. But the image on the right there, I absolutely adore. That is Michel when he just found out that he had been awarded the Nobel Prize. I believe he's at Madrid airport when that happened. And so I think the look on his face says it all, but it was very well deserved. And this was the very start of the field of exoplanets as it is today. And this was, this is a very recent thing. 1995 is not very long ago. And so it has been a very, very rapidly expanding field and extremely interesting. So when I tell people, oh, yeah, I find planets for a living, that's what I do, this is kind of what people expect that I look at every day, and that what I see. And you see all these wonderful artists' impression of what exoplanets look like. And I think they're absolutely wonderful. I love them so much. But this is what's portrayed in the media. And often we will work with artists to ensure that we try and get an accurate depiction of what we might expect the planet to look like. But we don't know that it looks like this. And we certainly are not receiving data that looks like this, I can absolutely assure you. And I've already been guilty in my time already of showing you a handful of artists' impressions that are not representative of what we look at. Well, what we really find in general, and this is just one example, is something like this. So this is an image from the European Southern Observatory, or ESO, from 2005. And this is actually an image, the first confirmation of the first ever directly imaged planet. And so the sort of big blob on the right there in blue, that's the host, and that's it was actually orbiting around a brown dwarf. And so again, this is a very interesting system because it's not orbiting around a solar type star like our own star. This is a very interesting, widely separated. So 55 AU, as it's written there, 1 AU is the distance between Earth and the sun. So multiply that by 55 times, and that's how far away this planet is from its host. And so again, this is by no means a representation of a potentially habitable planet or anything, but this was an extremely exciting detection of the first direct detection. It was originally discovered in 2004, but it was ambiguous about whether it was co-moving with its host or not, and then it was confirmed in 2005. So really, these are a bit more representative of the kind of images that I look at day to day. So how do we actually go about finding these planets, right? How do we hunt for these distant worlds? So there are many different ways that we can do this. And the first of those I would like to describe to you today is the radial velocity method. And so this was actually the method that was used to discover 51 Peg B by Michel Mayor and Didier Queloz in 1995. So I think this is an extremely exciting one to kind of start off with. So what we observe is, as this star, which is shown in the center there, shining away, and then a companion or a planet orbiting around their center of mass. And so it's not that the planets just orbit around a star, even though it may seem that way when we look at the sun and we look at the planets orbiting around the sun. It's just that the star is usually so much more massive than the planet that the center of mass is so close to the star that it's essentially as if the planets are orbiting around or close to the center of the star. But in fact, actually, the planets, even true in our own solar system, tug on the star, or on the sun in the case of the solar system. And so as they orbit around their center of mass, you kind of get pulled in this general direction, as you can see that's going on here. And in this way, we can indirectly measure that there's a planet in this system. So we don't directly see the planet. What we measure are the stellar spectra, and we can measure the spectral lines of the star, and we know where we expect those spectral lines to sit. And as the star gets tugged by the companion or the planet, then it will move towards us and away from us. And in this respect, we call this a Doppler shift, or it gets red shifted and blue shifted. And we can measure how fast this is happening. So we can measure like the orbital period of the companion as it orbits around the star. And we can also measure things like the mass or the minimum mass of the companion that we're looking at indirectly. And so I think a clearer way to see it is with this animation here, where again, so on the left, we have the star represented by the yellow circle, and then the planet represented by the blue circle. And there's just two different orientations there. So either we're looking at it face on, or we're looking at it edge on. And we don't necessarily know what the orientation would look like. But in this case, so you can see it's orbiting around the center of mass. And then we have the stellar spectral lines or representation of them in the bottom right there as they get blue shifted and red shifted. And then what we measure is the velocity, the radial velocity, hence the name of the technique of the star. And then that corresponds to the amount of time it takes to do this full kind of period that you're seeing there with the yellow dot going along its curve. That's like the orbital period, or how long it takes for that planet to orbit around the star. And so that would correspond to how far away the planet is away from the star. And then also that speed is proportional, or is a function of the mass of the object. So a more massive object would have a much larger radial velocity curve. So I mentioned before that 51 Peg B was discovered using this method. And as you can see here, this is the original radial velocity curve that was published back in 1995 by Michel Mir and Didier Queloz. And as you can see, we have this really neat radial velocity curve that's been measured. And we can see that full orbital coverage, which is really exciting. You can see the error bars on each of the measurements there. So that's the radial velocity technique. And this has been a pretty successful technique in terms of discovering hundreds of exoplanets over the recent years. But another technique that is also that has also been extremely successful and continues to do so is the transit technique. And so the transit technique works by we observe a star. And again, this is another indirect method of searching for exoplanets. We're not observing the planet itself. We observe a star and we know how much brightness we're receiving from the star, the flux. And as a planet transits, like we just seen there in front of the star, then we get this dip in the brightness that we receive from the star over time. And then this corresponds to how long it takes for the planet to travel across the star. And so that can give us an idea of what the orbital period is like, or what the separation is like. And then we can also measure the radius of the planet by doing this. And so this is an extremely powerful technique in order to understand what the composition of exoplanets is like. Because if you have an idea of what the mass is like and what the radius is like, then you can look at the density and you can compare it to, is it dense like a rocky planet like Earth or Mars? Or is it less dense like a gaseous planet like Jupiter, for example? And so this has been the most successful detection technique of exoplanets to date. And part of that has been due to Kepler. So Kepler was launched back in 2009 and operated by NASA. And Kepler was a space telescope that was extremely successful at staring at the sky for long periods of time in different campaigns in different regions of the sky in order to look for these transits. And so it was kind of dubbed the kind of Kepler era in the exoplanet fields, as we suddenly received thousands of exoplanet candidates that corresponded to transits that had been measured using Kepler. So when we look at transiting exoplanets, one of the things is we get different dips in the brightness corresponding to the different planets or the different stars we're looking at. So first of all, if we look at, let's call this a solar type star, it's the same radius as the sun, then we might get this kind of dip from the black planet shown there going in front of the star. But if we're to observe a much smaller star, which there are many of in the universe, and we call these M dwarfs, then what we see is if the same size planet orbits in front of that star, then we get a much, much bigger dip in the brightness that we measure. And that is far easier to measure than the same size planet around a bigger star, like, for example, our own sun. And so, and you can see it in the dips on the bottom there on the over time. And so this kind of led people to move towards more looking around M dwarfs and these smaller and smaller stars to kind of look for transiting exoplanets. And so in 2017, very famous system called TRAPPIST-1 was actually announced that kind of went along these lines. So these planets, and these are all in the same system, these 7 planets orbit around an M dwarf star. And so it was kind of this approach of, okay, if we look at a star that's much smaller, then we'll be able to detect the signals of more Earth-like, smaller rocky planets that would otherwise be much, much more difficult to detect. And so this was outstanding. This was 7 Earth-like planets orbiting in the system. And you start to think, okay, so this is really interesting. This is something that kind of resembles, or almost resembles, our solar system. And if you look at the transit curve, and this is from 2015 when the first 3 planets were discovered before the rest of the system was discovered, then you can see this really neat transit curve of all 3 of those as they go across their star. And so it's not always this one sort of neat dip that I showed you before, but you can get like numerous planets that are transiting within themselves. And you can see along the bottom there, so these correspond to the planet names. So 1E, 1C, 1F, those are the names of the planets as they travel in front of the star. And you can kind of get this really, really cool transit curve. So like I say, transiting exoplanets has been an extremely powerful technique in order to discover thousands of known exoplanets to date. But another detection technique is actually the microlensing technique. So the way that this works is you have a telescope, and you see at the bottom there, observing a star in the distance, and then this planet that kind of moves in the front of it, and it acts as a lens when it does this. And you can see in the bottom right there that over time we get this peak in the brightness as this happens. And so again, this can be a really, really powerful and compelling technique in order to find these kind of planets. It was a little bit more difficult because you need that chance alignment. So, you know, there's a difficulty in that. But when you observe it, then these things have really strong signals that we're able to detect. And so I'll just show another animation here from NASA that kind of shows a similar thing. And so what we see on the right is kind of what I showed you before, where you have that lensing effect as the planet moves between the telescope and a background object. And then in the center is what you maybe expect it to look like if you were looking face on, as if you were the telescope. And then on the left is what you kind of expect the microlensing event to look like in terms of the brightness over time and what we see as scientists when we look at the data. And so it looks something like this, where you kind of have that magnification by the stellar lens, and then you get that deviation due to the planet. And so this is a really awesome technique in order to use as well. And Space Telescope Science Institute will be launching the Nancy Grace Roman Space Telescope due to launch in the mid-20s, which will be really amenable to this kind of technique in order to find lots of micro lensing events. And it will also be amenable to finding lots of planets to direct the image, which brings me to my next technique that I will describe. So I'm a little bit biased about this because direct imaging is what I primarily work on. And so I will deem it to be the best exoplanet detection technique, which is not necessarily true, but that's how I will take it. And so direct imaging kind of, it does exactly what you expect. It does what it says on the tin, that you are directly imaging a planet. And so the other techniques I've shown you before have all been indirect methods. They've been what happens to the star or to as a result of the star, and the signals that you observe from that. But in this case, we're actually not interested in the star. We're trying to remove as much of the starlight as possible and look directly for a planet around that star. And so this has led to some really interesting, awesome results over recent years. And so what I show here is on the left is HR 8799. Unfortunately, planetary systems don't have very exciting names, but this is its catalog name. And in this case, we have 4 exoplanets that are orbiting around the central star there. So what we're actually looking at is in the middle, you've got that's the star, that's the stellar host. And that's being masked out. We're not interested in the light from the star. We want to suppress as much of that as possible, but that's where the star is. And then you kind of see these 4 blobs orbiting anti-clockwise, counterclockwise. And those are the 4 planets that we see. And again, as I told you at the beginning, what do you expect an exoplanet to look like versus what we actually observe? It is just a blob of pixels, but there's a lot of information that we can pull out from this. And the GIF I'm showing on the right there, that's from Bates Pick, which is another very famously imaged system where you can see it being observed there just before it goes behind its stellar host. So these wonderful animations have been made by Jason Wong, who you should go check out his webpage. And he has a whole bunch of these, but we're not actually observing this isn't being observed in real time. These are many different epochs of data that have been put together in order to generate these movies. So you can see the dates there on the bottom run over several years this isn't actually what we observe immediately. This has to be strung together over a very long period of time to understand what the orbital motion looks like and to confirm that the planet that we're looking at is actually connected with the star that we're observing. So the way this kind of works is we have to take into account lots of different factors. This is not an easy thing to do. Otherwise, people would just do it, right? So the magnitude, the brightness of the star compared to the brightness of the planet is huge, millions of times. So you really, really need to remove as much of the starlight as possible. And we have the added difficulty when we do this from the ground using ground-based telescopes, which I'll speak a bit more about as well. But we look and we stare at a star and we hope that it has a nice friendly planet next to it, like in this little image. And then in the case that we're doing ground-based observations, we have to take into account for the Earth's atmosphere. And we do this using adaptive optics, which I'm going to explain. But this is essentially like putting a pair of glasses onto a telescope. And then the other really, really important thing is using what's called a coronagraph. And so coronagraph is the thing, the mask that sits in the middle that blocks out as much of that starlight as possible. And so you can imagine if you were looking up to the sun, you shouldn't actually do this, but if you were to look up to the sun and put your thumb in front to cover the sun, to cover the sunlight, and you would see like the corona of the sun around the outside of it. And that's where the name coronagraph comes from. We basically do the same thing. It's like doing that on a telescope, putting your thumb up to remove as much of that starlight as possible. And then you kind of just get the residual starlight that's left around there. And then this comes in through a detector as shown by a camera there. So because this is so difficult to do, because the contrast ratios that you're talking about between the star and the planet are really, really extreme, then often what we do is we end up discovering what's called brown dwarfs. And so brown dwarfs are in this mass range that sit between, they're less massive than the star. So a star is an object that can fuse itself. It's massive enough to undergo hydrogen fusion, but a brown dwarf is more massive than a planet. So a brown dwarf is massive enough to fuse deuterium in its core. And so it sits in this kind of obscure in between space where it's not quite a planet, it's not quite a star. But these are so much more massive and brighter than planets that these are far easier to detect not just with direct imaging, but certainly with direct imaging, but also with radio velocities and things as well, if they're close to the star. And we kind of get a lot of these objects that sit in the middle. But I do want to emphasize the importance of actually observing these things. So I know you came here for an exoplanet talk, but in order to understand how exoplanet atmospheres work, brown dwarfs are excellent analogs to do this, because they possess very similar atmospheric properties to planets, but they're so much easier to detect. And so we can use these as analogs to try and sort of calibrate our exoplanetary atmospheric models of formation and evolution as well. And so I really love this excerpt, which was in the New York Times. Face it, in this town, either you're a star or you're just another brown dwarf. And this was kind of the view when brown dwarfs were first discovered, because it was like, they're kind of in this in-between stage, like, you know, this in-between mass range. How interesting is that? Well, actually, over the recent years, it's discovered how important they really are in order to understand exoplanetary atmospheres. And so I move on to another detection technique, which I'm also a very big fan of. And this is the use of astrometry. And so again, this is another indirect method of finding exoplanets and looking at how the companion that you're trying to detect affects the orbit of the star that you're observing. And what happens is we stare at a star as it and the path of this star moves across the sky over several years. And so we kind of get this linear path, and that's due to stars moving through the galaxy. And then we also get this kind of spiral motion, and that's just due to us observing from the Earth as we move around the sun. So it kind of appears to go in this spiral-like motion. But we know the astrometry of these things, of these stars, very well. And so if we notice any perturbations between the star and the path that we expect it to take, which we can see that's represented by this sort of brown orange color on there, then those perturbations can be caused by an orbiting companion. And so it's kind of, so it has a similar essence in the detection technique to the radial velocity technique, but it's using the position on the sky rather than just the star itself and how it's radially moving. And so in order to look at the astrometry of such things, there have been some telescopes in recent times that have enabled us to do this. So for example, Gaia, which is an ESA satellite that was launched in 2013, has been mapping out the astrometry of stars since 2013 when it was launched, and has been doing an incredible job at understanding the astrometry of these stars. And also prior to that, it was Hipparchus, which was another ESA satellite that was launched back in 1989, and has been another really powerful satellite in order to enable us to kind of use this detection technique. And the most powerful thing is combining the two of them together in order to understand how the astrometry of these things changed over time over the past 20 years or so. So great, we can observe and we can detect all of these wonderful things and make all of these wonderful discoveries, but like, what is it that we can actually detect? Like, is this representative of our own solar system? Are we trying to understand how these things form and evolve? And so what I really wanted to emphasize here was the first discovery, you know, going back to Michel May and Didier Queloz with 51 PeG-B or 51 PeG-CB. And what we can see here is the comparison of the radius and the mass between Earth, our own Earth, Jupiter and our solar system, and 51 PeG-B. And as you can see, 51 PeG-B in the middle there is huge. It's bigger than Jupiter, which is our largest planet in the solar system. And this planet sits really, really close to its host star. But this is why it was far easier to detect than being able to detect, for example, an Earth-like planet, because the signal, the radial velocity signal that we observe is much more massive when you're observing a more massive companion. So of course, but this baffled astronomers when it was discovered, because we were not expecting to discover a Jupiter-like planet so close to its star, because that's not how our own solar system is like. So the first extrasolar planet that was discovered kind of blew a lot of theories of formation of our own solar system out of the water, and kind of led to an array of trying to understand how planets form and evolve. And this is, we're amenable to detecting kind of different companions based on different detection techniques, just because of the way that the different techniques are set up. And so what happened after 51 Peg B was discovered, and what was then this kind of term that was coined hot Jupiter, and that's because it's a Jupiter-like planet that's so close to its star, so it would be far, far hotter than Jupiter. It's a hot Jupiter. And after 51 Peg B was discovered, there was a whole array of so-called hot Jupiters that were discovered using the radial velocity technique, which are very amenable to finding these hot Jupiters. And again, this kind of continued to baffle how these things formed and evolved. If we look at like the number of planets that have been discovered over the years and how that's changed. So what we're seeing here is the kind of mass separation parameter space of planets and exoplanets that have been discovered through all time. So to this point, in up to 1995, we can just see the solar system planets that are put onto there. So along the x-axis, we have the orbital period, and that corresponds to how far away that planet is away from its stellar host. And then we have the mass on the y-axis there, so the more massive ones sit at the top and less massive ones at the bottom. And yeah, so what you can see here is the green points on there at the moment. Those just correspond to our own solar system, planets from our own solar system as they were discovered across the 1700s. And then we hit at 1995, where there was this boom of exoplanets and the field exploded, literally. So we can see that the different colors there correspond to the different detection techniques that I've described to you earlier. So we have the radial velocity ones, we have the transit ones, we have the microlensing ones, we have the imaging ones. And you can see they kind of probe different populations, right? So the ones that are much, much further out at much higher, longer periods, those are the imaged ones, because it's far easier to directly image something if it's further away from its bright stellar host. But the ones that are closer to the stars are the ones that are detected using transits and radial velocities. Radial velocities produce much higher signal if the planet is very close to its star. Transits, you're much more likely to detect them if they're close to their star. And so it's interesting that you can kind of get all this different probing of different masses and different orbital periods, and building up this picture over time of what the exoplanet distribution actually looks like. And this is going to be really exciting going forward as we continue to find more and more exoplanets and understand where the observing bias ends, and whether how these things actually form and evolve. And so to date, there have been more than 4,000 exoplanets discovered. And this is just going to continue to increase over the next few years or so, and into the next few decades. Okay, so now that you're all experts on how to find exoplanets, you need the instruments, you need the telescopes to be able to do this. So what makes a good telescope, right? So first of all, we need giant mirrors. So telescopes typically use mirrors and refract light to a focus point in which we can actually observe. And this is kind of contrary to popular belief when I speak to people who think that we have these giant lenses, but it's just so difficult to do that. And mirrors are much more efficient and much, much lighter in order for us to be able to do this. But what we see here is if we compare a much larger mirror versus a much smaller one, then we kind of have the light path going on there and where they come to a focal point. And what we call the angular resolution, so actually being able to observe between two different objects, like two different stars, for example, is much, much higher if we have a much more giant mirror. And so that's why we kind of reach this point where we build a bigger telescope, and a bigger telescope, is to get that angular resolution that's required. And that's really important when you're doing direct imaging of exoplanets, because to be able to observe a planet that is close to its star from direct imaging, you have to have the biggest mirror possible. And so the European Southern Observatory, or ESO, are currently building what's called the ELT. And so astronomers are really bad at naming things, but the ELT stands for Extremely Large Telescope. And you can see an artist's impression of it here with Big Ben next to it. Very British of me, of course, but you can see just how big this telescope is going to be and how big that dome is going to be. So this is going to be a game changer when this is on sky, and it's currently in the middle of being constructed. A couple of years ago, I actually had the pleasure to be invited to the construction site of the ELT, and this is what it currently looks like, or maybe it's a bit more built up since I went. You can see me stood in the middle there, and this is the foundation of where the dome is going to sit. So this is 40 meters across and about 130 feet or so. And this is going to be a huge, huge telescope that's going to be a great game changer in the field of exoplanets. But another thing we have to take into account, and I kind of mentioned this before, is the Earth's atmosphere. And so when you look at the night sky and you see all this really nice twinkling of the stars, this isn't due to the stars themselves. This is due to the effect of the Earth's atmosphere and observing the stars through the Earth's atmosphere. So although it looks very pretty, for any astronomer that's using ground-based observations, this can be extremely annoying because it can blur our images and make it very, very difficult to resolve things. So even if you have the most giant mirror possible, if you can't correct for this, then you're still going to have a very, very blurry image. And so the way that we correct for this is with adaptive optics. So the way that this works is we have a plane wavefront that comes in from observing some stars or galaxy or whatever it is we're observing. And if we were just in space, it would just be this plain wavefront. But because we have to observe through the atmosphere of the Earth when we're doing ground-based observations, the turbulence in the Earth's atmosphere causes this plane wavefront to then be perturbed into this corrugated wavefront that then enters the mirror of the telescope. So we can see the light beam entering there, coming in through the primary and secondary mirror of the telescope. But we can correct for this. And the way we do that is we take a little bit of light away as it's observed using what's called a beam splitter. And then this is fed into a wavefront sensor. And so this wavefront sensor reads what the wavefront is that we've just observed coming into the telescope. This is read into a real-time computer. And then this is looped back out to the mirror that can be corrected to cancel out the perturbed wavefront that's coming into the telescope. And this is extremely exciting, awesome optics that I really, really love. And so the remaining wavefront, after it's corrected, then goes through into the camera where we have a high resolution image, which is what we want. And so this continues to loop through. And in the cases of large telescopes where we have adaptive optics or extreme adaptive optics, this happens at tens of thousands of times a second, so kilohertz. And this is extremely important for us to get those really high resolution images that we need in order to do things like direct imaging of exoplanets. And what you can see on the right there is you go from looking at something where the intensity of the light that we're looking at isn't extremely high and isn't extremely well focused, to looking at something that has this nice sort of pinprick of high intensity light that enables us to look at those high resolution images. And you see the difference that it makes. And this image is from ESO. So they actually observed Uranus a couple of years ago now, I think. And you can see the image on the right is without adaptive optics. And this is a planet in our own solar system. So this, in theory, shouldn't be the most difficult thing to do if we're comparing to the observations we take for planets outside of our solar system. But as soon as you turn on the adaptive optics, you can see there that you obtain that detail. And that's due to the adaptive optics allowing us to get that high angular resolution. We can also compare this when we look at stars as well. So this is also from ESO, and looking towards the galactic center, and turning the adaptive optics on from off. And you can see you go from that kind of blurred image there to that much cleaner, crisper image. So this is really, really important for us to be able to do this. So where do telescopes sit? You know, where do they exist around the world? So here I'm just kind of highlighting some of the most renowned, largest telescopes across the globe. And really, we need to put telescopes in places where we have low light pollution. So you don't want to put a telescope in the middle of a city, of course, because that makes it much, much harder to see fainter objects. So all of these are pretty remote locations. You also need somewhere that has good weather. You don't want to deal with rain or clouds because you wouldn't be able to observe through through those things. And you also want somewhere that has a really low humidity as well, because that can take away from the light that we're receiving. It can absorb at those wavelengths that we're trying to observe at. And then, of course, that makes our images even more difficult to look at. You also want to be in a place that has as stable atmosphere as possible. So you don't have to correct using adaptive optics as fast as if you were in a place that has a really, really unstable atmosphere. And so those places are often high up on mountaintops where you have less atmosphere to observe through. That's why these observatories tend to be at high altitudes. And also at mountains where you have kind of this optimal configuration of like flat landmass, so or ocean, and then kind of a sudden rise up to like a mountain. And so that's why places like Hawaii or along the Andes or the Atacama Desert in Chile are really ideal places to have these telescopes to observe. So we're able to detect all of these wonderful planets. How do we hunt for aliens, right? That's the big question. That's the question that everyone always asks me and wants to know the answer to. So it's not just about detecting planets, but it's about understanding them. And so I've spoken a little bit about understanding their formation histories or the evolution of them. But how do we also understand like their composition or their atmospheres, right? And how do we find the most ideal place where we might expect to find life? So first of all, we'll look for something called the habitable zone. And so the habitable zone is kind of this Goldilocks zone where a planet orbits we're in a place that it's not too hot that you can't have liquid water, but it's not too cold that you can't have liquid water. So you don't want the water to be gaseous or non-existent, but you don't want the water to just be frozen. And so obviously our own Earth, where we have plenty of water, we sit within this habitable zone, this Goldilocks zone, in the separation away from our own star, the sun. And so here what you can see is we have the sun, and then we have each of the planets in our solar system. And if you go so far away that we've kind of got these gaseous, cold planets that would not be ideal for life, they also don't have solid surfaces and things like that. But then if you go too close to the sun and you're too hot, like Mercury and Venus, then you kind of have this difficulty of being too hot to be in this like habitable zone. And so Mars kind of sits on the edge of that habitable zone, and there's kind of a question about whether there used to be life on Mars or not. But when we look at exoplanets and we look at these systems, we kind of try to look, is the planet we're observing, does it sit within that habitable zone? And it's not to say that if we observe a planet in the habitable zone that there's definitely life on that planet, or even that there's definitely water on that planet. There are many different factors that come into this, like its own atmosphere and things. And water does not necessarily mean that there is life on that planet. But this is just a strong indicator that there could be. Because if there's one thing that we agree on is that all life on Earth has this kind of water base one way or another. And so this can just be a strong indicator for how we look for planets that may host some form of alien life. And recently in the news, there was a report of the molecule phosphine on Venus. And so this is really exciting because this is a molecule that is difficult to exist or almost impossible to exist without there being, for example, life or something that is causing it to exist. And so I won't comment too much on this, but this is even trying to understand the atmospheres of the planets within our own solar system, with our own neighbors, can be an extremely difficult thing to do. But this is a really exciting result that's kind of being followed up and trying to be understood. But I think it's a really worthwhile thing to think about. So how do we actually look at the atmospheres of these planets? So I'm going to take you back to the transiting technique that I told you about earlier. And what we can do is we can observe in different wavelengths when we observe the transits of these exoplanets. And this is different wavelengths there corresponding to 1.8, 2.1, 2.3 microns. So that's just across different wavelengths. We can measure the depth of the transit at each of these wavelengths. And because certain molecules in an atmosphere will observe at certain wavelengths, then we get different depths when we observe in these different wavelengths. And that can give us clues about whether we're observing a certain molecule in the atmosphere of something we're looking at. So this is a really powerful technique in order to do this. So that's transmission spectroscopy. But if we go to the emission spectroscopy side of things, which is what I work on. So again, we can take you back to direct imaging of a companion. And so we see on the left is beta pic and the direct image of it. And what we see there is as we go across the different wavelengths, so we're observing at lots and lots and lots and lots of different wavelengths, the plot on the right there corresponds to how much brightness, how much flux we're observing at each of those wavelengths. And so the emission of those things can correspond to different absorption features that can be caused by certain molecules, for example, methane, or water. That is another way to look at the atmospheres of exoplanets. And what can be really exciting as well, and I've stolen this from Exoplanet Pete, so I hope that's okay, but go and follow him on Twitter, is you can look at the different like altitudes in the atmosphere that correspond to the different pressures and temperatures in the atmosphere, and how the spectra that we look at, so the flux or the brightness that we're observing, looks at different wavelengths. And so we can get these kind of stronger molecular features as we go to like colder temperatures, for example, where we kind of expect those methane and things like that. So this is a really, really cool technique. And this is very much at the beginning of looking at exoplanet atmospheres. This is still a very young, early field, as I said previously. And so we're really just starting to get to this point of understanding how we can do this, and using, like I said before, brown dwarfs are a really strong analog that can be used and much far easier to detect directly in order to help us understand and calibrate our models of exoplanetary atmospheres. So this is very much a stay tuned as we kind of investigate how we do this well. So just wanted to mention a couple of, obviously the trademark of Space Telescope, Hubble Space Telescope that was launched back in 1990, which has been responsible for observing many of these wonderful planets and brown dwarfs that I've mentioned today using these kind of techniques, and continues to be a massive player in observing the atmospheres of these objects. And what's even more exciting is the upcoming James Webb Space Telescope, which will be launching later this year. And this is going to be an incredible feat of engineering that will enable us to look even at even more exoplanets and look at the atmospheres in even more depth and truly understand what it is we're looking at, and to try to understand the formation and evolution of planets, both of exoplanet systems and planets in our own solar system. And so James Webb will has this incredible sun shield that you can see, the big gray kind of sun shield there, that's going to open up to protect it from as much of the sunlight as possible. And then it has this huge mirror that is going to open up hopefully well, and hopefully everything will go well. And so this will be a really exciting thing to follow over the next coming months after it launches. And so with that, I will wrap up. And I just want to say, you can be a planet hunter too. There are many interesting citizen science projects that are related to exoplanets. I've just highlighted two here that are both set under the Zooniverse links. But you can go to that website and you can have a play around. And we've had people, just non-scientists, members of the public, who have ended up being on published peer-reviewed journals because they've helped to find signals in our data using these projects. And so I strongly encourage you, if you are interested in this kind of thing, that you should go ahead and check out those websites and do go and do some planet hunting. And with that, I'm happy to take any questions that you may have.
Thank you, Emily. That was wonderful. And we have had an amazing number of questions and comments on our chat today. You really, you touched a lot of people here today. This was great. Let me ask the first question, which sort of kind of always comes up when you talk about the radial velocity technique. Because you showed that, you mentioned that, the sun and Jupiter are pulling on each other. And so our sun does wobble too. So the natural question that people often ask is, hey, would aliens out there in space be able to detect our planets when looking at our sun with Jupiter's motion causing a little bit of wobble in the sun? How would our solar system look to some alien astronomers?
Yeah, that's a fantastic question. So there are some people that work on this, that kind of observing the sun as if it was an exoplanetary system. And the answer at the moment is no, it would not be possible if they had the same telescopes and the same instruments as us, just because the precision that you need of the radial velocities is so high that it's just, Jupiter is so far away from the sun compared to the typical systems that we look at, that the signal is just so small, but you need that really, really fine precision. But we're just reaching that tipping point now. And so there's this spectrograph which measures radial velocities called Espresso, that was just put onto the VLT in Chile, which is at Paranal Observatory, and is kind of just starting to reach that precision that would be required to do that. And so assuming that the alien life that would be observing us, or the radial velocities of our sun, had access to that same precision level instrument, then yes, they would be able to, but they would have to have that technology in order to do so, yes.
Right. That's great. Because that also touches on another question that people had, is just how fine are these radial velocity shifts? When you show those animations, they tend to be really big and it's obvious so that the public can see it. But these radial velocity shifts are really, really tiny. We had to develop several new techniques in order to be able to find these, just when we first did it back in the 90s, right?
Yeah, absolutely. And so we're really starting to push down towards the 10 centimeters per second precision. That's insane. Measuring a star at 10 centimeters per second, that's in another system, however many light years away. And the techniques that are required to do this are absolutely incredible. And the technology that has advanced so far in just a short period of time in the past 20 to 30 years has been absolutely incredible. So like I say, this new spectrograph Espresso has been doing just that, and it's going to continue as we go towards the ELT, which I mentioned before. It's going to be incredible.
Okay, yeah. So just for everyone's reference, astronomers are used to measuring things in kilometers per second, all right, in terms of velocities, and then this getting down to 10 centimeters per second, that's factor of 100 increase and such. And so this is just like amazing. So Emily, why don't you stop your share screen? And let's bring in Grant Justice. Grant has been monitoring the chat a little bit more carefully than I have. And I'm sure Grant has found a number of really cool questions for today. So what do you got for us, Grant?
Yeah, we have had a really great chat today. So thank you all for participating and being here for the live part. As a reminder to everyone, it will be up again afterwards if you did miss any part of it, including the Q&A. So starting us off, and this one I really like, what are ways that you could see exoplanets or extrasolar, whatever it might be, planets' bodies in the future based on what we are doing here today?
I think that we're going to see a real combination of all of these different measurement techniques come together. So all of the different detection techniques that I mentioned, I think they're all so with the radial velocities, we're going further and further out to longer and longer orbital periods. And on the imaging side, we're coming further and further in towards smaller inner working angles closer to the star. And I think things like that, where we're going to end up combining all of these different detection techniques. And that is really powerful, because from each of the different detection techniques, you get different characteristics of the planet that you're looking at, or the orbital characteristics. So for example, with radial velocities, you only get the minimum mass because you don't know the orbital inclination of the system that you're looking at. It could be face on or edge on. But if you combine that with direct imaging, for example, you remove that degeneracy and you're able to fit for the orbital inclination. And so I think what's going to happen over time is, and I was showing that detection map earlier with all of the different planets, is all of those are going to kind of like shrink in together, and we're going to be able to have all of this incredible information, these really well characterized exoplanets. And that's going to be really important to understand the mass, the radius, to look at the atmospheres of these things and really reveal the truths about what we're looking at. Because often when we get the detections, we're like, okay, we're looking at something that's however many Jupiter masses thing that's maybe this far away from the star, and that's all we can really say. But when you combine it all together, that's going to just change the field of exoplanets massively.
So, Emily, what about the idea of a star shade that was proposed for various space telescopes, that we float out a shade to act as a coronagraphic spot, basically floating out in free space things? Is that going to happen? Because that offers quite a bit of advantage.
Yeah, I mean, I say let's do it. Like, fund us, NASA and ESA, if you're listening, whoever has the money, please give it to us. That would be fantastic. I think another exciting thing is going to be potentially putting a telescope on the moon, on the far side of the moon. I mean, you wouldn't have to deal with the atmosphere of the Earth. You wouldn't have to deal with light pollution. I think that would be an incredible thing to do as well. So yeah, I think there's lots of exciting technology that's being, concepts that are being thought about, things like these star shades that, of course, it always comes down to funding, but this would be a game changer as well. Yeah, absolutely.
All right, great. What else we got, Grant?
All right, so next one up, and this is one we get asked a lot about HST, because everyone wants to know why it can't observe our own universe, our own galaxy images or bodies that are closer to it. What are some of the complications that you have on the opposite end of the spectrum with searching for exoplanets, searching outside of the solar system?
I think you just broke up for a minute there, or I broke up for a minute there. Would you mind just repeating?
Sure. There are a lot of things that we deal with and a lot of things we talk about with HST because it's long range observing, short range, like in system. What are some of the challenges that you have with the existing telescopes observing exoplanets, observing long range?
Yeah, so one of the specific difficulties with HST is just the wavelength coverage for exoplanet science. So HST is perfect for many different types of subfields in astronomy, but with exoplanets, we tend to observe in the longer wavelength range, so sort of towards the very long end of the optical into the infrared. HST doesn't really, it's not optimized to probe that wavelength range. And that's going to be the big game changer with JWST and exoplanetary science, because we've got a handful of instruments on there that are really going to target that wavelength range. So like NIRSPEC and NIRCam and MIRI, they're going to be fantastic in probing those longer wavelengths that's required to do the science that we want to do. I mean, also bearing in mind that HST was sort of the concept of HST and the launch of it was way back when there were only a handful of exoplanets had even been discovered. And of course, these missions take years and years and years to design and put together and launch. And so it probably wasn't even at the center of the scientific output that was being thought about when you think about HST. And so JWST is going to be a game changer. And there's also other mission concepts that we're thinking about, like HabEx and LUVOIR, which are NASA mission concepts that are going to be probing those wavelength ranges that are more amenable to observing exoplanets.
And you mentioned adaptive optics in your talk, and that's really helping ground-based observatories approach what we can see from space. But generally, I mean, this is at infrared, correct me if I'm wrong, but I've always understood it to be basically at infrared wavelengths and over a relatively small field of view. How is that progressing? And where do we see that going in this discovery?
Yeah, so it's primarily over the visible and infrared wavelength range. It's so the kind of concept of adaptive optics is now being taken into space, even with the Roman Space Telescope, and so it is that technology is then being enhanced to something like corrections for, not obviously for the atmosphere, but in order to actively correct the optics for a telescope in space. So I think the technology that's being worked upon, improved upon, and researched down here on Earth is now being used to refine our space images even further. And the technology that we're able to do with this, like increase the frequency at which we make these corrections. And the attenuators that are on the mirrors is kind of increasing over time. The reason you have to do this primarily in the visible and infrared is just because that's where you get the most kind of refraction from the Earth's atmosphere when you observe those wavelengths. It's not an issue if you're observing, for example, in the radio wavelength range, because you're not affected by the refraction. Yeah.
Right. And the idea of a multi-mirror telescope like James Webb was, we were just starting multi-mirror telescopes in the 90s, right? The 80s and 90s. So none of that even could possibly have been thought of for Hubble, which launched in 1990.
Absolutely. Exactly.
One of the things that the comments were talking about quite a bit are the differences between HST and JWST and Roman and so on and so forth, and the interactivity between them and HST and JWST, because there is a little bit of overlap, but they observe like different spectrum like ranges. They actually can work in concert, which is what we were telling the chat. But that brings us to another one, and this immediately made me think of the nano apertures. But how are like physical barriers used in the telescope for like lithography machines or minimizing light interference? So that's basically the whole concept, but if you would like to elaborate a little more.
Yeah. One of the most interesting concepts of this will be the giant sunshade on JWST, and that is going to be a huge thing, and we're all going to be crossing our fingers and praying and hoping that this all goes smoothly. Not that we have
a long 2 weeks
to believe otherwise. Yes. But yeah, so definitely utilizing things like this in order to remove as much of the sunlight as possible. And yeah, you have run into different issues of things like HST, where it's orbiting in low Earth orbit, and but then you have to deal with the breathing of HST as it goes in and out of the sun. It expands and shrinks down because of the thermal energy it's receiving from the sun. So yeah, but I'm extremely excited to see the starshade be deployed and how this goes, and hopefully everything will go as smoothly as possible. Yeah.
All right, and I'll go to this one next before I lose it in the chain of comments. What is your personal favorite or most interesting mystery about exoplanets that you have found thus far or would like to solve?
That is an amazing question. I don't know if I thought too long and hard about this. Yeah, so I'm very biased towards the upper end of planets, upper like mass range of planets and things, just because of the stuff that I primarily work on. And so I think I'm a secret lover of the gas giants, planets that are a lot more like Jupiter and things like this. And I'm just hoping that we find some really interesting, obscure, like atmospheric properties of a planet like that have some really, I don't know, maybe strange molecular features or things. So that's what I see as an exciting thing. More in general, though, I hope within my lifetime that there is some strong evidence to suggest that there is life on another planet. That would be the most incredible thing to live through, and I really think that we're getting closer and closer to that revelation. So yeah.
Okay, so I'm going to say that I kind of am really, really, really intrigued by the super Earths. Okay. Yeah. All right. So we're starting to see the categories of planets that we see in our solar system replicated out throughout the universe, but there's these 5 Earth mass objects out there, and I'm like, well, that doesn't fit with what we've got here. That's a whole new class of planet. These mini Neptunes or these super Earths. So I don't know which we want to call them, but that's the kind of ones that intrigue me the most, because it's like, this is something brand new. And so when we get statistics on that and really start to understand those, I think that's going to be, that's going to be an eye opener.
Yeah, I completely agree. And I'm really looking forward to seeing how that shapes and evolves our own views on our own solar system. Like, are we really unique in the way that our own solar system is set up? Or as we go towards being able to observe more of these things, are we more representative of what an average stellar system looks like? And I think that Super F1 is a great question that's involved in that, because we just don't have anything like that in our own solar system.
Absolutely. All right.
It's true. All right. Continuing on from where we are. Sorry, I'm looking at multiple screens here. So first off, shout out to you from Space TV. They are looking forward to the launch of the Emily Rickman Space Telescope to study gas giants.
That would be incredible. Someone please fund me.
And secondarily to that, and this is something that's already ongoing, but I would like for us to elaborate a little bit more for the people in the audience who haven't seen it. There's another talk all about TESS and a lot of the efforts undergoing to catalog planets that we want to point at later, kind of like a range finding sort of satellite, which I find infinitely interesting. But a lot of that is already going underway. So would you elaborate a little bit more about the classifications of planets, of exoplanets, and like what specifically we look for? And I know infrared will help us with atmospheres and whatnot, but everyone wants to know a little bit more about the search for like habitable worlds and what that looks like.
Yeah. So I think categorizing is a really is an interesting way to put it. Yes, I actually didn't mention TESS, but that's just because I ran out of space on the number of space telescopes I could mention in one talk. But yes, TESS is the Transiting Exoplanet Survey satellite, and it has a very similar job to Kepler, but on an even bigger scale. And actually, one of the links I put on the very last slide, if people want to get involved with this, is actually looking at TESS light curves. So if people are interested in that, then absolutely go and check that out and be involved in it. But yeah, so TESS is doing a huge job of looking at thousands and thousands of both new exoplanets and ones that have, it's staring into the sky to find both stars that maybe that we know already host planets and also new planets. And those kind of statistics that we've got from Kepler, but also TESS, are really enabling the categorization of those planets, because you can't categorize something that you have like 10 planets for. Like, it doesn't mean anything. And so we're really starting to get to this point now where we can say, okay, this thing has a composition that's similar, it's rocky, it's similar to Earth or something like that. And what I was saying before, that you could get the radius from the transit technique and masses by combining like radial velocity information, for example. So that's really important. And once you've got that constraint on the mass and the radius, and you can get an idea of its composition, of its density. And so the categorizing is going more beyond what it used to be of like, oh, this thing is this certain size. It's now like, oh, this thing maybe has this kind of atmosphere, or this thing has this kind of composition. And it's really trying to understand that also the connection between that as well, between the composition and the atmosphere. And that's something that's kind of new. But yeah, so as Frank mentioned before, super Earths is a category of these giant Earth-like planets that are really incredible and are a bit of a mystery to us. And then the interesting thing I find with the categories is where you kind of draw the line at hot Jupiter. So the Jupiter-like planets are extremely close to the star. And then the warm Jupiters. And then you start to go into like warm Neptunes and hot Neptunes. And one that really annoys me is when people start saying cold Jupiters, but they mean something that's maybe has an orbital period of a few years. When I say a cold Jupiter, I mean something that has an orbital period of tens of years. And so there's still a bit of a discussion within the exoplanet astronomy community about how we even really categorize these things. But yeah, TESS is really driving forward a lot of that, because it's such a big survey satellite. It's able to stare, has a really wide field of view. It's able to stare at a lot of stars. It's able to kind of constantly monitor a lot of these things. And that will also be true for the Roman Space Telescope as well.
Yeah, and what I really love about talking about those satellites is that you can see the succession of the missions, in that Kepler really stared at one spot in the sky and got lots and lots of statistics to say, all right, well, how many of these exoplanets do we expect out there? And then TESS does follow up, and it's all sky, and it's looking all over the place, and it's getting the closer ones, but it's finding the ones that James Webb can then follow up and study in detail, because almost all of the stars with exoplanets found by Kepler are too far away for Webb to study. But the ones found by TESS will be perfect for Webb to study. And so that's the succession of these missions and way they work together. That's exactly how we planned it out, and it's working out great.
Yeah, that kind of mission optimization is really interesting to watch, and has sped up a lot in well, at least for the optimization of exoplanetary science, as we've seen with the mission concepts with Habex and Livoire, as you would really, they designed to go span across many different wavelengths across a wide wavelength range, and we just don't really have that at the moment on one telescope. So those will be game changers that hopefully come about in the future. And not too distant future, hopefully.
Not too distant, yes.
Yeah.
Right.
All of the telescopes working together and everything was where I kind of wanted to get this, because I mean, we take it for granted in the astronomy community, but different missions by different agencies and whatnot, there's a lot more working together than you would think from the outside looking in on a lot of these projects.
Okay, Grant, we got time for one more question. You got
Okay.
you got one last one?
No, I'll leave that to you, Frank.
No, I don't have one.
Oh, you don't have one. Okay.
I think we've gone through all the ones I notated.
Okay. All right. So, oh, here we go. Once they are located, they can be studied for atmosphere. Not well to some extent now, but obviously once James Webb launches and we're able to look further into the spectrum, that will be a case. That's more or less what we just talked about. Here's a good one. How long after the launch of James Webb can we start to expect to see any data or any studies?
So there's going to be a commissioning period. Well, first of all, the telescope, James Webb Space Telescope, has to get to its Lagrange point, and then it has to deploy its sun shield and its mirrors and everything else, and then we'll go through a commissioning period, where all of the instrument teams will make sure that everything is up and running as expected. And then we're going to be on early release science. So the first data coming through will be plus 6 months or so after launch. Don't quote my exact number on that. I'm sure someone who works for JWST is screaming at me right now. But it will be about 6 months or so after launch. Will be when the first data starts coming through. Yeah.
And don't worry, you can hear our anxiety from miles away during that period.
I have my own anxiety about it. It's all fine. Everything's gonna be fine.
We will all have our lucky talismans and our ways to deal with all this. Yes. Actually, I did find a question that I wrote down that
bring it on.
Pretty good. It says, when a planet is in tidal lock with its star, how does that affect the chances for finding life on that planet?
Yeah, that's actually a really interesting question. So in that case, you would have a planet that's orbiting very close to its star, and so close that it gets tidally locked. So one side is always staring at the star and the other side is always staring out from the star. But the problem with that is the side that's tidally locked and staring at the star is going to be super hot and super probably inhabitable. And then on the other side, you're going to have very much the opposite problem, where you're going to have this extremely cold side that's potentially not habitable. So it's a little bit more complicated than that, but these aren't the most amenable planets to look for habitability. The conversation is a bit more complex than that, but that's kind of the bottom line, is probably not the best ones to look at. But yeah.
Yeah. Okay. That's fantastic. All right. So, Emily, fantastic talk, fantastic subject that we will be revisiting over and over again through the public lecture series. Next month, on July 6th, Quinn Hart will be talking on Armchair Astrophysics Volume 2. Until then, keep observing your universe. Take care.